Hello everyone, I'm Chengyu Wang from Alibaba Group. Today I'm going to present our paper, Weakly Supervised Construction of ASR Systems from Massive Video Data. So building large-scale ASR systems is highly challenging. This is because it is time-consuming and financially expensive to annotate a large amount of audio data with transcripts. The data is used to train ASR models. Recently, self-supervised pre-training technique has been applied to ASR, but there is a learning gap between self-supervised pre-training and ASR training objectives. Some methods generate synthetic speeches aligned with the text for model training, but the generated speeches may still be different from real speeches. So in general, building large-scale ASR systems is a very challenging task. Our question is it possible to build accurate end-to-end ASR systems without much manually labeled data? Our answer is yes. In our work, we present a weakly supervised pre-training framework for ASR system construction. In the first stage, weakly supervised pre-training, we use videos as our data source, use OCR to extract audio and transcripts. Then we use the data to pre-train ASR models. In the second stage, we do domain-specific fine-tuning. So given a pre-trained ASR model, we have different domain data. So in each dataset, we use a small dataset to fine-tune the model to generate a domain-specific ASR model. So the first technique is called weakly supervised pre-training. So at first we do text and audio spotting, which means we extract audio from the video and we do optical character recognition, OCR, to extract the text. So we have audios and text. So next we need to do that we have a sequence of audio and text that they are aligned with each other, so we can use these data for training. So we have two kind of techniques. One is called heuristic-based approach. The other is called model-based approach. The heuristic-based approach uses rules to extract audio aligned with transcripts, and the model-based approach uses a commercial ASR system to do the recognition first, and then we use the generated result to compare it with the result from OCR, and we have this kind of data for model pre-training. And during the pre-training process, we do noise filtering to ensure that our pre-training data has high accuracy. The second technique is called domain-specific fine-tuning, as the domains of pre-training data may be significantly different from downstream ASR tasks. So giving a small training set of a specific domain, we fine-tune the pre-trained model to learn domain adaptive parameters, so we can generate domain adaptive ASR models for downstream tasks or applications. In our work, because we aim to construct an industrial large-scale ASR system, we consider two types of model architectures. The first is called wave-to-ladder, and the second is called speech transformer. In the wave-to-ladder architecture, we have log F-band features as input, and we have different convolution layers to extract the contextual features from the raw log F-band features, and we also have residual connections to make sure that the learning process is very smooth. Finally, we have fully connected layers, and the CTC loss is employed to minimize the training error of the model, so it can be applied for ASR tasks. The second architecture is called the transformer. So we have the encoder and the decoder During the encoder, we have the transformer encoder layers to generate the features. It includes the multi-head attention, the addition, and the layer normalization operations. And we also have decoder layers, which is highly similar to the encoder layer. And finally, we have two-part loss. The first is called the CTC loss, and the second is called sequence loss. The sequence loss is the final loss for the transformer, but we also use CTC loss here to ensure this is a multitask learning process to ensure that we generate highly generalized models for ASR. So this is two kind of model architectures. We can see that the wave-to-ladder model is simple and has high inference speed. The speed transformer model is somewhat complicated, but it's more accurate. So it both has cons and pros. In the experiment, we evaluate our framework using 6 public datasets and 2 models. So this is the data set statistics. We can see that this label data has different domains and different types. And in the result, we can see that our transformer model consistently outperforms state-of-the-art approaches. And we also find that with WSP, weekly super pre-training, our model has a large improvement for both wave-to-ladder and transformers. So it shows that our approach is highly effective without any pre-training steps. And we also compare to our approach to the transformer model with and without pre-training. Here, this pre-training means self-supervised pre-training. We can also see from the HKUS dataset that our approach is slightly better than the previously proposed self-supervised pre-training technique. Next, we have the convergence analysis on weekly supervised pre-training. And we can see for both models with weekly supervised pre-training, our initial error rate is relatively low, and it fast convergence to a steady point where we can use it for real-world applications. And the final error rate is also lower than the original model without weekly supervised pre-training. For error analysis, we can see that with the WSP weekly supervised pre-training technique, we reduce a lot of errors, especially for substitution and deletion for HKUST, showing that our approach can be more generalized to real-world datasets. Additionally, we have the industry deployment part. Our solution has been deployed on the ASR distributed machine learning platform in Alibaba Group. We have first further evaluated our approach on in-house e-commerce dataset. So we can see that with weekly supervised pre-training, the error rate of both models decreased significantly. And we also have the comparison between wave-to-ladder and transformer. We can see the transformer model has much lower error rate, but a long inference time. We suggest that we can use the wave-to-ladder model for fast online inference, while the speech transformer model is more suitable for offline inference. So the inference time wouldn't be a big bottleneck for real-world applications. In conclusion, in this paper we present VideoASR, the framework for weekly supervised pre-training ASR systems. We construct accurate ASR systems based on the weekly supervision of massive video data. This is fundamentally different from previous works, as previous works may use audio data or other sources, were among the first to use massive video data. In the future, we aim to apply our approach to other languages and other kind of ASR models, and combining unsupervised and weekly supervised pre-training for ASR. and we'll also explore leveraging transfer learning to improve the model fine-tuning process. Thank you for your attention, and if you have further questions, you can directly contact us via email. And thank you again for your listening. Goodbye.